Good evening, everyone. I welcome you all to the problem solving session of NPTEL course on ice engines and gas turbines. So, this is the first problem solving session from me. I'm Pradeev E. I'm one of the TA for this course. So, my sessions will happen on all Tuesdays 6 to 8 pm. So, there will be some 12 sessions in total. I will be solving some previous assignment questions and also some questions from other books. And this video will be recorded and it will be uploaded in YouTube, and the link of the YouTube will be given in the NPTEL portal, and also the problems that I am solving, like this screen where I write everything, will be uh, uploaded as a PDF in Google Drive, and that link will also be available to you. So if you have any questions, you can stop me in between, but I request you all to mute before, otherwise. So if you do not have any questions, you can mute. Only when you have questions or when you want to answer something, you can unmute yourself and answer. Do you have any questions, or we can go to the questions problem? Okay, I will start with the problems. The first question is, thermal efficiency of a heat engine is defined as dash net work output by heat in output, or net work output by total heat input, or total heat output by net work output, or total heat input by net work output. Or some, if you know your answers, you can either put in the chat box, or you can also unmute and tell me. So what is thermal efficiency of a heat engine? Can you answer? Second option. Second option is right. So generally you write efficiency as output by input. Here for an heat engine, the output is work and input is heat. The flow around a household fan can be assumed as supersonic, hypersonic, compressible, or incompressible. So, can you answer this? Flow around a household fan can be assumed as supersonic, or hypersonic, or compressible, or incompressible. So flow around the fan is incompressible. How do we define this? Is like when the Mach number is less than 0.3, we call it incompressible. Do anyone know what is Mach number? Yeah, so Mach number is actual speed, or the fluid speed, right? by speed of sound at in the fluid medium. So that is called a sonic speed. So for air it is around 330 meter per second, and this will be much less than the the flow around the household fan will be much less than 330, and it will be less than 30% of it. So it is incompressible flow. So then supersonic flow is when Mach number is greater than 0.3 but less than 1, it is called as subsonic, and Mach number greater than 0.3 is called compressible flow, and Mach number greater than 1 is called supersonic. Mach number far greater than 1, that is like greater than 10, is called hypersonic. It is clear. Which of the following are the example of an internal combustion engine? Steam engine, Stirling engine, spark ignition engine, all of the above. SI engine. So why do we say like this? Why SI engine alone is called internal combustion engine among these? The combustion is taken inside the engine. Yes, correct. So in SI engine and say CA engine or a compression ignition engine, both things in both the engines, the combustion takes place within the engine or within the combustion chamber or the boundaries of the engine. Spark plug will be there, so combustion will take place within the combustion chamber. But whereas in case of steam engine, uh, within the within the system there is only a fluid medium like water, water steam, and in case of Stirling engine the medium is only air. So inside the engine there is only air or steam, but the combustion happens externally and heat is fed into the system. So these are called external combustion engine, and EC engine, and this is called IC engine. In a 4-stroke IC engine, the crankshaft rotates dash times in a complete working cycle. 2 times. So for a 4-stroke engine there will be 4 strokes, and for to complete 4 strokes we need to complete revolution of the crankshaft. So what are the 4 strokes? First stroke, second, third, fourth. You can also unmute if you feel typing taking time. Yes. So intake stroke, compression stroke, power or expansion stroke, and then exhaust stroke. So out of these 4 strokes, only this gives out power, whereas others will take uses the power of the engine, like the kinetic energy of the engine. So that is why we have a flywheel which will store the kinetic energy, and during the power stroke it stores the energy in kinetic form, and then gives out the energy for the taking care of the others. Which of the followings are the part of a compression ignition engine? Piston, spark plug, fuel injector, carburetor. Yeah. Here, part of fuel engine. So in a SI engine, we will have spark plug, and carburetor is needed to mix the fuel and air before it enters into the combustion chamber. So that is why we use a carburetor. So those are not part of combustion engine. Consider two single-cylinder engines having identical cylinder size. One of them is a two-stroke engine and runs at 500 rpm. The other one is a four-stroke engine and runs at 1000 rpm. The ratio of the theoretical power developed by the two strokes to the four-stroke engine is dash 0.512. Can you answer this? Two engines have identical size, but one is two-stroke, other is four-stroke. Two-stroke engine is running at 500 rpm, four-stroke engine is running at 1000 rpm. What could be the ratio of the power? Yeah, one. How? Can you answer how it is done? Okay, so same size engine, we can identical cylinder size, which with which we can say that power work done during compression and work done during expansion are same. So both will be same. Same for two-stroke and four-stroke. Now, um, now we need to know how much uh, cycles is happening for every second. So that is like for a two-stroke engine with 500 rpm, every rotation is one cycle. So 500 by 60 is the cycles per second. Similarly, for the other one, four-stroke engine, there are 1000 rpm, so 1000 by 60 rotations per second. But every two rotation is one cycle, so you have to put a 1 by 2 so that you get cycles per second. So both are same. Both has 500 cycles per second, and the work done per cycle is also same, and the number of cycles per second is also same. So the power output will be the same. That is how we got one. You have any questions? The indicated power developed by IC engine is 10 kilowatt. If its mechanical efficiency is 90%, the frictional power loss will be dash kilowatt. Can you answer this? 1 kilowatt. So this is 1 kilowatt. How mechanical efficiency is theta net is brake power by indicated power, and brake power can be written as indicated power minus friction power divided by indicated power. Now this is 10 kilowatt, sorry, this is 90% efficiency, that means 0.9 is equal to indicated power is 10 minus friction power divided by 10. So we'll have 10 minus friction power is equal to 9, that means friction power is equal to 1. To achieve large mass flow rate in an engine, the most preferable compressor is axial compressor, multi-stage, centrifugal compressor, centrifugal or reciprocating compressor. So for more mass flow rate, we prefer axial compressor, and more pressure ratio, we prefer centrifugal compressor, that we will be seeing later. To achieve large mass flow rate in an engine, the most preferable compressor. So just again. Steam turbines are used for these engines which work on Carnot cycle, Otto cycle, Rankine cycle, or Stirling cycle. Steam turbines working with cycle, Carnot, Otto, Rankine, or Stirling. Steam turbine runs with Rankine cycle. A simple carburetor is not capable of supplying correct air-fuel mixture for varying engine load and speed. This statement is true or false. This is true. During carburetor lectures you will understand. In a four-stroke SI engine, each working cycle is completed in dash revolutions of crankshaft 2. A compression ignition engine does not contain any of the following. Can you answer this? A CA engine does not contain carburetor, fuel injector. Yeah, carburetor. Anything else? Partner. It has fuel injector and combustion chamber. The cubic capacity of a four-stroke 8-cylinder IC engine with cylinder 4 D mm, stroke length L mm is given by dash. Pi d square L by 4, pi d square L, 2 pi d square L minus 2. 2 pi d square L. How? If you take volume, displacement volume of one cylinder, it is pi by 4 d square L. So now we have 8 cylinders, so volume of the total displacement volume of the engine is number of cylinders MC into VC. So number of cylinders is 8, so then we have pi by 4 d square L. So this is 2 pi d square L. The function of camshaft in an IC engine is to control the opening and closing of intake and exhaust valves, convert the reciprocating motion into rotary motion, drive the ignition system, all of this. Sorry, okay? No, this is camshaft. Yeah. Yes, A four-stroke single-cylinder IC engine having a cylinder bore d and stroke length L is called underscore when d is greater than L or d equal to L, d less than L, d square greater than L. Answer is okay. What is a square engine? Yeah, d is equal to L. And underscore engine? D square greater than D? D square greater than L? No, not D square. You have underscore and you have overscore. So for underscore, the combustion chamber is like this. This is D, so this is L, and this is D. So for a square engine, it is perfectly square. D and L are same. For uh, over square engine, it is a rectangle like this. So that means D is greater than L. For underscore engine, it is a vertical rectangle like this. So that is D less than L. So now we want underscore, so underscore is D less than L. Which of the following engines can be categorized as IC engine? Steam turbine, Stirling engine, gas turbine, open cycle, gas turbine, closed cycle. Which of the following is IC engine? Steam turbine, Stirling engine, gas turbine, open or closed. We have already seen steam and Stirling are external combustion engine, and among gas turbine, which is external and which is internal? Open cycle is internal combustion, and closed cycle is external combustion. In open cycle is similar to a aircraft engine, where fresh air is taken in, the fuel is combusted into inside the engine, and then exhaust is sent out. So this is open cycle because the fluid, the working fluid is not brought back in a closed loop. So it is an open loop or open cycle. In a closed cycle, like similar to a steam turbine, there will be only heat addition from outside. Combustion will happen externally, and then heat will be added to the working fluid and taken to a gas turbine. So that is closed loop cycle, closed loop gas turbine, which is external combustion. So now the answer for IC engine is gas turbine open cycle. The Wankel engine is a rotary internal combustion engine, reciprocating spark ignition engine, reciprocating compression ignition engine, or stratified charge engine. Have you seen a Wankel engine earlier, or like the image of a Wankel engine? there is a rotary internal combustion engine. The combustion chamber is something like this. So air will go in and spark will occur here. So this rotor is the shape is mantle and this rotates, and when it rotates the air is sucked in, and then here when the chamber comes to this region it will be compressed and ignited, and then when it comes this region it will be expanding, and then here it will be open to the exhaust. So this is mantle engine. So this is a internal combustion engine, but it is not of reciprocating type. There is no reciprocating components. It's all rotary components. For identical size of engine operating at the same speed, two-stroke engine is usually more fuel efficient than a four-stroke engine. This statement is true or false. This statement is false because two-stroke is actually less efficient than a four-stroke engine because the HC or the fuel will be short circuited and goes to the exhaust without burning. Most of the fuel goes like this. So that is why two-stroke is less efficient. But when compared to the power output, two-stroke will be twice the power of the will give a twice the power of a four-stroke engine for the same engine speed. So that is what we saw earlier. Compared to a four-stroke IC engine, two-stroke IC engine does not have any separate suction, induction, compression, power, exhaust stroke. Can you answer this? So the two-stroke engine does not have suction, induction and exhaust stroke. It has only compression and power stroke. Next question, consider the following statements regarding two-stroke IC engine. The process of exchanging the incoming charge and combustion product is called scavenging. This is true. The scavenging process controls the efficiency of a two-stroke engine. Yes, because if the scavenging is very poor, it will be short-circuited and we lose more of efficiency. It can be either spark ignition or compression ignition type. Yes. It does not contain any intake or exhaust valve. Yes. So all of the above are correct. Do you have any questions? I just want to get to know some basic introduction about yourself. Can you just one by one unmute and say like where are you from, and if you are a student, or if you are a student which semester you are in, BTech or MTech, or if you are working somewhere, you can uh, let me know like what is your education qualification and what is the point of you doing here, like what you want to learn from this course. Uh, can you one by one unmute and yeah, right. Yes. Okay. Okay. So you are crediting this course for your semester, or this is just you are taking out of your interest? Hmm. Yes, sir. Okay. I am from IIT Madras. If you know from the place, from IIT Madras, so you can also, if you are more interested in visiting our labs and all, you can mail me and then contact me.
Okay, sir.
Thank you. Right.
Sir, I'm Divyansh from SMU University from Jammu.
Okay.
Currently, I'm in my third year semester. I planned on taking the course earlier, but it is also a part of semester credit, so I thought I should take it.
Okay. So which university you are from?
Shri Mata Vaishno Devi University.
Okay. Next, you can see many names. Known as Deva Kumar, Kumar, Kumar,
Myself is I am from Siddhartha Engineering College.
all the things. Okay. Which semester you are in?
I am second year.
Second year. Okay. So you are crediting this as a part of your degree or?
It paid to our college.
Sorry?
It pays to the college.
Okay. Sorry. Anyone else wants to introduce? For those who joined just now, I'm just asking a brief introduction about yourself. You can unmute and then tell your name, where are you from, if you are studying in a college, which year or semester you are in, and if you are crediting or you are just taking this course out of interest. If you are working, then it's kind of something you are working on. If no one else is interested, then we move on to the problems.
Hello, sir.
Yes.
My name is Mohammed Tawaran.
Hmm.
I'm UG student in the final year from mechanical engineering.
Hmm. Which university?
Usmania University.
Sorry, Anna University.
Usmania University.
Usmania.
Hyderabad.
Okay, Hyderabad. Okay, okay. And you are crediting this as a part of your curriculum or this is separate?
This is separate, sir.
Okay. 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 Nice. Thank you. Anyone else wants to introduce? Yeah. Hello. Yeah. 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 I can hear you. Hmm. Hmm. Okay. Hmm. Part of curriculum. Okay. Yeah. Okay. Okay. Fine. Fine. Thank you. Okay. I think I didn't tell about something. So I am a PhD student in IIT Madras and currently doing my fourth year PhD. And my work is in hybrid powertrains, developing hybrid powertrains for two-wheeler applications. And currently I'm in fourth year. So I'm from IIT Madras. So if you are anywhere around and you want to meet in our lab, Ice Engines lab, you can mail me and then we can fix a date and we can meet. Yeah. Okay, then let's start with the next problem. Cubic capacity of a 4-stroke over-square spark ignition engine is 245 cc. The over square ratio is 1.1. The clearance volume is 27.2 cc. Calculate the bore stroke compression ratio of the engine. So over square engine means we saw D is greater than L. So D is greater than L. So that means D by L is 1.1. So that is D is equal to 1.1 times L. And we know the cubic capacity, that is displacement volume. So cubic capacity is displacement volume, that is pi by 4 d square L is equal to 245 cc. Now if you put d as 1.1 times L, we will have pi by 4 1.1 times L whole square into L equal to 245. So we will have L cube is equal to 4 into 245 divided by pi into 1.1 square. So L is cubic root of S. So when you calculate the value of L, so it is better you always have a this scientific calculator with you, so it will be very helpful in solving the problems. So yeah, once you calculate, you can either unmute and tell the answer, or you can also type in the chat box. Sixteen point zero five. I am getting 6.36. Can you check 1 second? Then we know D is 1.1 into L, so that is 6.36. That will be this D. Yeah, approximately sound, that is 6.996 centimeter and approximately 7 centimeter. Then we can calculate the compression ratio. What is the formula for compression ratio? Yes.
Soap volume by soap volume by compression volume. Air volume.
Subvolume plus clearance volume by clearance volume. So now we know soft volume. V displacement is also soft volume. So we know soft volume is 245. Sorry. Something. So soft volume is 245 and clearance volume is 27.2. So with this we can calculate clear compression ratio.
Yes, and box.
Yeah, 10.057, we can say 10.0. Any questions, or we can move on to the next topic? The mechanical efficiency of a single cylinder four-stroke engine is 80%. The frictional power is estimated to be 26 kW. Calculate the indicated power and brake power developed by the engine. So mechanical efficiency is given as 80%, that is 0.8. What is mechanical power?
250.
Mechanical efficiency is brake power by indicated power. So what is brake power and indicated power? You would have gone through the first week lectures, right? Okay. Brake power is the, sorry,
So the power of the machine.
yeah, so that is a power that we can feel in the shaft, or it can also be mentioned as shaft power. And what is indicated power? So this is like the torque that comes out of the shaft. So if you connect a load between the engine and the torque transmitted from the engine to the load is the torque. So that comes as, or it can also be set as brake torque. And omega, that is the speed of the engine. So based on these two we can calculate some power, and that is brake power. And what is indicated power?
So brake power plus losses.
Yeah, brake power plus loss. So here it is friction power. So what is so this is a summation of these will give indicated power, and indicated power as such can be explained by uh, so the gases on inside the combustion chamber will always exert a pressure on the piston, and this because of this there will be because of the pressure of the gas we will exert a force on the piston, and this will can develop this is capable of developing a power. So this will develop a torque on the force on the piston, and this force can be downward force can be transferred to a torque, and that is called indicated torque. And so this is indicated torque. Why it is called as indicated is in olden days to measure the pressure inside the combustion chamber, they take it to a system. They have an opening, and then there will be some system indication system that will have a spring and say a pencil kind of thing. So the spring movement will be proportional to the pressure inside. So when the pressure is high, the pencil goes or the marker goes upward, and then when the pressure is low, the marker goes down. So finally we will get some pressure curve like this. So this paper will, and this will be some crank angle. This paper will keep rotating, and crank angle. Crank angle is this angle, so theta. So there will be some gear system between this and the paper. So the paper will be on a cylinder and rotates, and there will be some indication system that will have a spring, and then the spring will ensure that the displacement is proportional to the pressure inside the system. So that is why, and with this only we can estimate some power output of the engine, and that is indicated power. And that is that doesn't have consider any friction between the piston and the liner, and also the these bearings, piston pin bearing, crank pin bearing, and the crankshaft bearings. These frictions are not considered in this indicated power. But after all these frictions, then we take shaft output power, and that is called brake power. So that is the difference between indicated power and brake power. Now, so I said this is indicated torque, and similarly we have brake torque that can be measured on the shaft, and the difference between this is again friction torque. Indicated torque minus brake torque is equal to friction. So similarly same thing applies for the power. So indicated power minus friction power is brake power. So with this we have atomic is equal to 0.8, that is brake power divided by brake power plus friction power. So brake power plus friction power is estimated as 25 kilowatt. So now we can calculate brake power. So here we will have 0.8 times brake power plus 25 is equal to brake power. Then 0.8 into 25 is equal to 0.2 times brake power. Then this is brake power is equal to 4 times 25, that is 100 kilowatt. Similarly, indicated power is brake power plus friction power, that is 100 plus 25, this is 125 kilowatt. This is clear. You have any questions in the problem?
So here, what kind of friction we are taking for only cylinder and piston friction, sir?
Yes, so this will consider all the frictions between the, I mean, yeah, from the piston, pin, connecting rod, everywhere. It will consider all the frictions. We summarize everything as a single term called the friction term.
Okay. And
Yes.
that indicator torque, sir, can you tell once again the indicator torque?
Indicator torque. Yes. So um, here on there is some gas pressure exerted on the piston, and because of this piston and this gas pressure will exert a force on the piston, and this force based on the slider crank mechanism can transfer a torque on the shaft, right? So this downward force will exert some force based on the angle, and similarly based on this angle this will exert a normal force like this, and that will be responsible for torque. So this force Ft or Ft into the radius, that is a torque. That torque calculated based on the gas pressure is called indicator torque. This doesn't consider any friction component, just only based on the gas pressure.
Okay, sir.
So ideally, if we have a system where there is no friction, uh, we have made these surfaces such that the friction is very negligible, then brake torque will be equivalent to indicator torque. But in real case, it will not be. We cannot make frictionless surface. So we want to know how much we are losing in friction. So that is why we have a term called mechanical efficiency. So in this case, the mechanical efficiency is 80%, means 20% of the energy obtained from the gas is lost in friction. So maybe uh, the designer can think of improving this to say 85%, 90% by designing a good frictional surface and good lubrication system. Any other questions?
Sir, your 20% is we are losing in the friction, or that is included in the 80%, sir?
Uh, so say 100%, sorry, 100 joules of energy comes from the indicator or the gas pressure, that is indicated. 100 Newton meters. So out of which 20% is lost, 20 Newton meters is lost in friction. And the torque that we see on the shaft, feel on the shaft, is only 80 Newton meter brake torque. So if you have the speed, then it can be the same. So 100 kilowatt indicated power, then some 20 kilowatt is lost in friction power, then remaining 80 kilowatt can be felt as a brake power.
Okay, sir.
Sorry? Sorry, Ganesh Kumar, can you mute yourself? So I hope there are no other questions, and we'll move on to the next problem. Someone has a question?
Yes, sir. We will go to the next question.
42.5 kilowatt engine has a mechanical efficiency of 85%. Find the indicated power and frictional power. If the frictional power is assumed to be constant with load, what will be the mechanical efficiency at 60% of the load? Okay. So 42.5 kilowatt engine means brake power at 100% load is 42.5 kilowatt, and mechanical efficiency at this case is 85%, it is 0.85. Now we need to calculate the indicated power and the friction power. So we know this is brake power at 100% load by indicated power at 100%. So this is indicated power. Yes, Ganesh Kumar, you have something to ask?
So what is brake power at 100% load?
So now we are dealing with different load conditions. So the second case is at 60% load. 100% load means this is the maximum that the engine can provide. Okay. That is 100%. So 50% load means half of this load condition. So Ganesh Kumar, you said you are absent. Yes, understand. You can you understand this problem? Anyway, the meeting, this will be recorded. Yeah. The session will be recorded. The video will be available. Will be uploaded in YouTube, and the link will be sent to you by through NPTEL portal. And similarly, this the notes will also be available as PDF format in a Google Drive, and that link will also be available in the NPTEL portal. So indicated power is brake power by 0.85. Brake power is 42.5 divided by 0.85. Answer this. Indicated power at 100%.
For 50.
Yeah, 50 kilowatt. And friction power will be 50 minus 42.5.
So 7.5.
Now they have mentioned that the friction power can be assumed as constant with all the load conditions. So now we need to find the mechanical efficiency at 60% of the load. So 60% of the load BP 60% is 0.6 times of brake power at 100% load. So that is 0.6 into 42.5. That is this.
25.5.
Yeah, 25.5 kilowatts. Now we know what is the friction power. So now we can calculate the mechanical efficiency. So mechanical efficiency at 60% load is brake power at 60% load divided by brake power at 60% plus friction power. Okay, this together constitutes indicated power. Brake power at 60% is 25.5 divided by 25.5 plus friction power. That is friction power is 7.5. Calculate this.
0.00.
So this is 0.75 or 77%. So you can see the mechanical efficiency has dropped by say 8%, because the friction power is same across all the load, but the power output is reduced. So according to this brake power, friction power, we will get reduced mechanical efficiency. Do you have any questions?
Yes, sir.
Moving on to the next problem. Find out the speed at which a four-cylinder engine using natural gas can develop a brake power of 50 kW working under the following conditions. So we know brake power is 50 kW. Air gas ratio is 9:1. Calorific value of the fuel is 34 megajoule per meter cube. CV of the fuel is 34 megajoule per meter. Compression ratio is 10:1. Volumetric efficiency is 70%. Indicator thermal efficiency can be written as ITE is 35%, and the mechanical efficiency is 80%. Total volume of the engine is V displacement. Displacement is 2 meters. So we need to find the speed at which the cylinder has to operate. So now we have brake power. Brake power is torque into omega. Omega is in radian per second. So we have to compute torque so that we know the brake power. This we need to find. Once we know the torque, then we can solve the problem. So this we can start using the indicator terminal efficiency, ITE. Indicator terminal efficiency is indicator power divided by fuel power. That is 0.35. Indicator power is not known, and fuel power has to be calculated. Then we have mechanical efficiency, which is brake power by indicator power. So indicator power is equal to brake power by mechanical efficiency. So here brake power is 50 kW and mechanical efficiency is 0.8. So it is indicator power.
$62.5 kilowatt.
Yeah, 62.5 kW. And for this we can plug it here. Then we will have fuel power is equal to indicated by 0.35. That's it. Indicated is 62.5 divided by 0.35.
What was 98.57?
178.57. So this much kilowatt we have. So Now we know this kilowatt is needed, and the calorific value of fuel is given. It's 34 megajoule per meter cube. So we can calculate how much of fuel flow rate should be there to get this power output. So we have fuel power is equal to flow rate into calorific value. Right? So fuel power is 178.57. I'm writing everything in the same, so this will become into 10 power 3, and then flow rate I do not know, I would write it as Q, and into calorific value is 34 megajoule per meter cube, so that is 34 into 10 power 6 joules per meter cube. So Q can be calculated as 178.57 into 10 power 3 divided by 34 into 10 power 6 joules per meter cube. So can you calculate this?
5.25 into 10 raised to power minus 3.
10 power minus 3. Can you say what is the unit of this?
Meter cube per second.
So here we have on the left hand side fuel power, we had kilowatt that we have converted to watts, so that is joules per second. On the right hand side we had flow rate into joules per meter cube. So finally we'll get this as Q as joules per second by joules per meter cube. So this will be meter cube per second. So now we have got the flow rate of the fuel, and next we can calculate how much fuel can enter in one cycle, because we are given the volumetric efficiency is given, the displacement volume is given, and air gas ratio is given. Based on all this we can calculate how much of fuel or meter cubes of fuel can enter in one cycle of the engine. First based on volumetric efficiency and the displacement volume, you can calculate the air entry in diesel. So I would say volume of air per cycle can be given as volumetric efficiency into V disc. So volumetric efficiency is 70%, 0.7 into V displacement is 2 liters. So we will have 1.4 liters. So for every uh, cycle of the engine, 1.4 liters of air can enter inside. Sorry, 1.4 liters of air and fuel can enter. So because this natural gas engine is a SI engine, so it will go as air and fuel together. So that is why we are given a air fuel ratio. So what we calculated is air fuel mixture, or I will write this as V mix. Now V mix is some volume of air plus some volume of fuel, and volume, this ratio is given as air gas ratio, that is 9 is equal to volume of air by volume of fuel. So now we know VA is equal to 9 times VF. So V mix is V air plus V fuel. So V air is 9 times of V fuel, right? V air is 9 times of V fuel. So this is 10 V fuel. So this is 1.4 liters we saw. So VF is 1.4 by 10 liters. So 0.14 liters of fuel, 14 liters of can enter the cylinder in one engine cycle. But we need 5.25 into 10 power minus 3. So 5.25 into 10 power minus 3 is minus in meter cube will be 5.25 liters, right? So we need 5.25 liters per second of fuel to develop the record power. Given. So that means engines cycles per second, or engine cycles per second should be 5.25 divided by 0.15. Can you calculate this?
37.5.
Yes, 37.5 cycles per second. Now can you say what would be the engine speed? So for every 2 revolutions we will have one cycle. So that means if we have 37.5 cycles per second, we will have 2 times of this 37.5 revolutions per second. And to convert this into RPM, we multiply by another 60, so that will be 60 into 2 into 37.5 RPM. Can you compute this? Yeah, 4500 RPM. So that means this is the engine speed needed to develop the given power of a 50 kilowatt with the given conditions outside, this air gas ratio, calorific value, volumetric efficiency. This problem seems to be lengthier, but it's all based on the basic concepts. Like you need to know what is a brake, what is integrated thermal efficiency, mechanical efficiency, and then how calorific value and power are related, air gas ratio and power. I will just go give a small recap, and then if you have any questions, you can ask later. The problem is to find out the speed at which a four-cylinder engine using natural gas can develop the brake power of 50 kilowatt working under following conditions. Air gas ratio is 9 is to 1, calorific value of the fuel is 34 megajoule per meter cube, compression ratio is 10 is to 1, volumetric efficiency is 70%, indicated thermal efficiency is 35%, mechanical efficiency is 80%, and the total volume of the engine is 2 liters. Now, starting with the mechanical efficiency, we know mechanical efficiency is brake power by indicated power, and brake power is given as 50 kilowatt. So, and mechanical efficiency is given as 0.8. So, based on this, we can calculate the indicated power as 62.5 kilowatt. Now, we know the indicated thermal efficiency is indicated power by fuel power. So, substituting the known values of the indicated power and the indicated thermal efficiency, we calculate the fuel power of 178 kilowatt. Now we know fuel power is flow rate of the fuel into the calorific value, and flow rate of the fuel I mentioned as Q, calorific value is given, and fuel power is just calculated. Put in everything in SI units. I calculate the flow rate of the fuel is 5.25 into 10 power minus 3 meter cube per second. So this is 5.25 liter per second. Now we know the mixture entering the engine, uh, considered as V mix, is volumetric efficiency into displacement volume. So volumetric efficiency is 0.7, displacement volume is 2. That means effectively 1.4 liter of the mixture can enter into the cylinder. Now V mix is comprises of volume of air and volume of fuel. Volume of the ratio between them is given as 9. So air gas ratio is 9, that is VA by VF. So now we know VA can be substituted as 9 times of VF. Then we will have uh, V mix is 10 VF, and V mix we just saw it is 1.4 liters, and so then we can calculate VF is 0.14 liter. So that means 1.4 liters of fuel can enter the engine cylinder for every one cycle of the engine. And we have also calculated that we need 5.25 liters per second of fuel to be fed to the engine to develop the given power. So based on these two values, we calculate the engine cycle per second as 5.25 by 0.14, that is 37.5 cycles per second. And with this, if you calculate the engine speed, it will be 4,500 rpm. You have any questions?
No, sir. But the fuel power series both are same, sir.
Fuel power is flow rate into calorific value.
So by the definition, both are different.
Yeah. Fuel power is like the power given to the engine, the power of the fuel given to the engine. So that is there will be some flow rate of the fuel, that will be say 5.25 liters per second, and every meter cube of the fuel will have some energy, that is 34 megajoule.
Okay.
Any other questions? If you do not have questions, I can go on to the next problem. A four-stroke, four-cylinder diesel engine running at 2000 rpm develops 60 kilowatt. Brake thermal efficiency is 30% and calorific value of fuel is 42 megajoule per kilogram. Engine has a bore of 120 mm and a spoke of 100 mm. Take rho A, that is density of air, is 1.15 kilogram per meter cube. Air fuel ratio is 15:1 and mechanical efficiency is 0.8. Calculate the fuel consumption kilogram per second, air consumption meter cube per second, indicator thermal efficiency, volumetric efficiency, brake mean effective pressure, and mean piston speed. So we have N as 2000 rpm. Brake power is equal to 60 kilowatt. Brake thermal efficiency is 30%. Calorific value is 42 megajoule per kilogram. Then bore diameter is 120 mm, stroke L is 100 mm, screw D is 1.15 kilogram per feet, air fuel ratio is 15:1, mechanical efficiency is 0.8. Okay, so first we can start by calculating the fuel consumption. We know brake thermal efficiency is brake power by fuel power. So here fuel power comparison is brake power by efficiency. So brake power is 60 kilowatt and brake thermal efficiency is 0.3. So we can calculate fuel power.
It's 200 sir. Fuel consumption.
No, this is fuel power. No.
Fuel power.
So now we know fuel power is equal to m dot f fuel flow rate into electric value. The last problem we solved it based on the volume because the calorific value was given in volume because it is a gas. So generally for liquid phase like diesel we mention in as liquid and mass. So fuel power is 200 kilowatt. Writing in SI units I have 200 into 10 power 3 and I have m dot f into calorific value is 42 megajoules, that is 42 into 10 power 6 joules per kilogram. So now we can calculate m dot f as 200 into 10 power 3 divided by 42 into 10 power 6. Compute this.
So it's 4.73 into 10 power minus 3.
4.76 into 10 power minus 3. What is the unit?
It is per second.
No, kilogram per second. Here we have calorific value in terms of kilogram. So fuel consumption is calculated. Now next is air consumption. So for air we know air fuel ratio is AFR is 15:1. That is m dot A divided by m dot F is 15. So that means m dot A is 15 times m dot F. That is 15 into 4.76 into 10 power minus 3. So that is m dot A. 0.0714. Unit is again kilogram per second, and we need to find the air consumption in terms of meter cube per second. So we have density as 1.15 kilogram per meter cube. So how do I calculate volumetric flow rate? It is m dot A by rho u. That is 0.0714 divided by density is 1.15. Can you complete this?
0.0621.
0.0621 meter cube per second. So we have calculated the air consumption rate as well. Next is indicator thermal efficiency. So we know the mechanical efficiency is 80%, and that is brake power by indicator power. So indicator power is equal to brake power by mechanical efficiency. Brake power is 60 kilowatts, and efficiency is 0.8. So you can calculate the indicator power. 75 kilowatts. So next is to calculate the volumetric efficiency. So we have already calculated the volumetric flow rate. Now we need to calculate the, so this is the actual flow rate, because we have calculated based on the actual power output and the calorific value and the actual distance. So this is actual flow rate. Now based on the cylinder size, we can cylinder size and the speed, we can calculate what should be the displacement volume rate. So that is the theoretical flow rate. So n, or first we can calculate q dot a theoretical is equal to v displacement into cycles per second. So that will be engine speed by 120. Correct. Now we know v displacement we have to calculate. So it is mentioned that it is a 4-cylinder engine with a given bore and stroke. So for a 4-cylinder engine, we have 4 into pi by 4 d square into L, and d square is the bore. I directly write in terms of cc, so this is 12 square into 10. Stroke is 10, 100 mm, so that is 10 into n by 120. N is the speed of the engine, that is 2000. So to calculate 2000 rpm of the engine speed to cycles per second, I divide by 120, because to for revolutions per second I divide by 60, and since it is a 4-stroke, I will have 2 revolutions for 1 cycle, so I divide rpm by 2, so that is n by 120. So this will give me the theoretical flow rate. Can you calculate this?
That is 25,000 into pi.
25,000 into pi. Can you get the final answer? 398.2 units.
It really shows centimeter cube per second.
Yeah, so cc per second. To calculate, convert this to meter cube per second, we should multiply by
0.0753.
So I have to multiply by 10 power minus 6. So that will be 0.0754 meter cube per second. This is rate of gas. Now volumetric efficiency is actual flow rate of gas by theoretical flow rate of gas. That is, actual flow rate is 0.0621 and theoretical flow rate is 0.0754. And calculate the volumetric efficiency.
82.36%.
82.3. Next, we need to calculate the break mean effective pressure and mean friction speed. So, what is mean effective pressure? So, we have this system here. So generally during compression the pressure inside the cylinder will go high, and during expansion it will from the peak pressure it will keep decreasing. So this can be represented in a PV plot like this, pressure volume plot. While starting from the section BDC, the pressure will be low and volume will be high, volume of the cylinder. As we sorry, I think I should stop right here. So section TDC, the valves are open, so the piston is moving downwards and the intake valve is open, so air is coming through the intake valve. So during this time the pressure inside the cylinder will drop a little below atmospheric pressure, atmosphere, and then reaches the BDC. At BDC again the piston velocity will be lesser, and because of that the pressure will again equilibrate. So this can be represented by a line like this, and during compression the pressure will keep increasing, and then after ignition and compression the pressure will start. At TDC it will be the around TDC the pressure will be the peak, and then during expansion the pressure will drop, the volume will keep increasing, and then after the BDC there will be some exhaust stroke where the pressure of the gas is pushed and the gas is pushed out. So because of this there will be a little pressure higher than the atmospheric pressure, and we have a pressure leak like this. Now we see that the pressure inside the cylinder is not constant, it is always varying during suction, compression, expansion, every time it is varying. Now and this is giving us a power called brake power. And if you assume some imaginary pressure which is applied through on the piston throughout, and this pressure is constant, and this constant pressure can lead to the same brake power. Assume the mean pressure that we apply gives out the same brake power, then that pressure is called as mean effective pressure. That is mean average, we are applying average, and effective pressure that is that gives the same effect as the varying pressure as it happens in an actual engine cycle. So this is called mean effective pressure. So this is we call it brake mean effective pressure, where this pressure is equivalent to the brake power that is developed, or it can be there is another term called indicated mean effective pressure, where this average pressure will lead to the same indicated pressure output. And yeah, so this is BMEP and IMEP. So now we need to calculate BMEP. Calculate that we can have brake power is equal to, we have a formula, so this is BMEP LAN. So this pressure will pressure into A is the area of the piston, will give a force. Pressure into area will give the total force on the piston, and that force into L will give the um, energy that is spent. So that is the work done by the mean effective pressure on the piston. So that is PLA, and N is the engine speed, and engine speed will be in generally in RPM, so we have it by 60, and this power output happens for every 2 cycles, right? So we divide by 2 here. So this is the formula for brake mean effective pressure. So BMP is brake power into 60 into 2 by LA. Brake power is 60 kilowatt. 60 into 10 power 3 into 60 into 2 divided by L is stroke is 100 mm, so I write it in SI units. It is 0.1 meter. Similarly, area is pi by 4 uh, um, bore square, so bore is 0.12 square into N is speed of the engine is 2000 rpm, and we have how many cylinders? 4 cylinders. So we will have into 4 plus L and A into number of cylinders. Can you calculate this?
$795.7.
7.5 774.7 Pascal. I think you are somewhere left. I think it is. Oh, maybe you said incorrect. So this is 7.95 and next is to calculate the mean effective pressure. Sorry, mean piston speed. So what is mean piston speed?
So the average speed throughout the service.
Yes.
Minimum.
So the piston will keep moving up and down in the strokes, and we know based on the slider crank mechanism the speed will not be constant, so it will be almost zero near the dead centers, both top and bottom dead centers. Around 90-degree crank angle it will be the maximum, and then again it falls. So this piston speed will keep varying, but we can calculate a mean piston speed that will uh, it's the same. If the mean piston speed is there, if we travel the same distance in the same time. So that is given by how do we calculate? So we know that it runs at 2000 rpm. So for every rpm, so for 2000 rpm we will have 2000 by 60 revolutions per second, and for each revolution how much distance the piston travels?
2 strokes, 2L.
2L, yeah? 2L. So 2L into 2000 by 60 meter per second. So mean percent speed is 2Ln by 60. That is 2 into stroke length is 0.1, sorry, 0.1 meters into speed is 2000 by 60. Calculate this. 6.667. So this is an 9%. Do you have any questions? No questions? Okay. If there are no questions, I can move on. Single cylinder four-stroke hydrogen fuel spark ignition engine delivers a brake power of 20 kilowatt at 6000 rpm. The air gas ratio is 8 is to 1 and the calorific value of the fuel is 11,000 kilojoule per meter cube. The compression ratio is 8 is to 1. If the volumetric efficiency is 70%, indicator thermal efficiency is 33% and mechanical efficiency is 90%, calculate the cubic capacity of the engine. So we know brake power is 20 kilowatt and speed is 6000 rpm. Air gas ratio is 8. Calorific value of the fuel is 11,000 kilojoules per meter cube. Compression ratio is 8. Volumetric efficiency is 0.7. Indicator thermal efficiency can also be written as eta IT, indicator thermal efficiency 0.33, and mechanical efficiency is 0.9. How can we calculate this? Any idea? How can I start?
So first we can calculate the indicated power by mechanical efficiency.
Yes. So indicated thermal efficiency is indicated power by fuel power. Okay, so we need to first have mechanical efficiency. Okay, so mechanical efficiency is brake power by indicated power. Yeah, mechanical is 0.9 and brake power is 20. So indicated power is 20 by 0.9. Okay.
22.2
kilowatt.
22.2.
Sorry. 22.2 kilowatt. And indicated thermal efficiency is indicated power by fuel power. So fuel power is indicated power by indicated thermal efficiency. Indicated power is 20.2 and thermal efficiency is 0.33. So I know what is the fuel power. Fuel power 67.34 kilowatt. And okay. So now what can we do? We have to
calculate
flow rate. Yeah. So Q is
fuel power upon calorific value.
fuel power by calorific value. Fuel power is 67.34 into 10 power 3 and calorific value is 11,000 into 10 power 3. So flow rate of fuel is
6.12 into 10 raised to the minus 3.
6.12 into 10 to the minus 3. Correct? 6.12, right? Now fuel flow rate we have calculated, then
So from air gas ratio we can find out the flow rate of air and gas.
so air gas ratio is QA by QF. So QA can be AGR into QF. AGR is 8 into fuel flow. This one into 10 power minus 3. So what is the rate of air? 8 into 6.12 into 10 power minus 3.
0.0488.
0.0854. That is 4 is make it cube per second. Now Q of mix is equal to Q of A plus Q dot F into 0.0489 plus 0.0069. What is the flow rate of mixture?
0.055.
Into cube per. So now we got the flow rate of mixture. Next, we can calculate cycles per second. So this is 6000 RPM, means 6000 by 120 cycles per second. So that means Q dot mix, sorry, Q mix, that is mixture that is needed for one cycle, would be 0.055 divided by 6000 by 120 meter cube per cycle. What is this?
Point zero zero
Meter cube per cycle. And now we know the volumetric efficiency. So volumetric efficiency is actual flow rate, that is Q mix, or actual yeah, that is entered inside divided by the displacement volume. So volumetric coefficient is known, that is 0.7. This is 0.7. So V this plus Qmax, that is 0.0011 by 0.7. Okay.
0.00157
157 unit
meter cube per second.
millimeter cube. We have Qmax is meter cube per second. So now we have meter cube per cycle of the displacement volume. Now it is a single cylinder engine, right? Single cylinder engine. Now we can, so this is a displacement volume. Can we write in liters? It's 1.57 liters. Okay. So if you have questions, we can see now, or I think it's already time. We can see in the next class. Okay, so if there are no questions, I will close the session. Thank
So
you.
we will have this every Tuesday.
Yeah. So I think there are 3 TAs like me. They have different timings. You would have got the mail. So my session will happen on every Tuesday, 6 to 8 p.m.
Okay.
Okay. So if there are no questions, I will close the session. Thank you for participating.